Okay, this is part 2 of Module 11, the chemistry of solutions. And so we're going to go over the remainder of this module, covering some stoichiometry, freezing point depression, and boiling point elevation today. So last week we went over some terms: solvent, solute, solution, and we talked about solubility. And we did 2 experiments last week where we saw the effect. The first was seeing the effect of temperature on solubility, and particularly what happens when you have a solid dissolved in a liquid. And if you guys remember from your lab, you dissolved sodium chloride in water and you heated the solution up to maximize the amount of solid that you could get into that solution. And we talked about that with a solid going into a liquid, you have to have space between the molecules of water to be able to get in between that sodium and chlorine to be able to have it go into solution. So if you increase the temperature, it's going to allow those water molecules to move apart a little bit further, and so you're going to increase the amount of solid. So, and then once we had heated the solution, we created a supersaturated solution of sodium chloride, but as soon as the temperature started dropping, you guys should have seen salt crystals start forming. And that was almost immediately. So what we can conclude from that is that as you increase temperature with solids in a liquid, your solubility increases, or the amount of your solute that you can get into a solvent increases. And as your temperature decreases, that solubility decreases. So it's directly proportional, or there's a direct relationship between temperature and solubility for solids in a liquid. So liquids in a liquid, pretty much same principle. As you increase your temperature, you increase your solubility. You decrease your temperature, you decrease your solubility. Now gases are another thing. In our experiment with the gas, so if you guys remember, we had the soda in a test tube. We put the soda in to cold ice water and let it sit there for a little bit. And you guys should have seen that the bubbles that are caused by the carbon dioxide that are dissolved in the solution of soda pretty much came to a halt. You didn't see a lot of bubbling, maybe just a little bit. But then when we transferred it over to the hot water, you should have seen those bubbles increase dramatically. Now, if you think about it, the reason this happens is that in the solution, in the solvent, as the temperature increases, those molecules get further apart. A gas wants to expand to fill up as much area as it possibly can. So if those molecules expand out, it can no longer trap the gas molecules. The gas molecules are lighter than the solvent, and they're going to rise to the top and escape. So gases in a liquid, as the temperature increases, solubility decreases. As temperature decreases, solubility increases. So it's inversely related to the temperature. So what about pressure? That's another thing that can affect solubility. And we weren't able to do an experiment with that, but with a gas, if we increase pressure, we can increase the solubility. And if you think back to your soda example, when you open a soda, the first thing you hear is a fizz. And that's because you're releasing that pressure, so your solubility immediately decreases and some of the gas escapes. So that's why carbonated things are bottled under pressure, to be able to get the maximum amount of carbon dioxide, so you have that nice fizzy soda. Now, pressure doesn't have an effect on the solubility of either liquids or solids. Neither one of them, it affects it at all. Okay, so let's talk a little bit about energy and solutions. And we're just going to briefly go over the 2 terms. Keep these in the back of your head because they'll come back in a future module, and we'll do some more calculations and stuff related to this. But the first is an exothermic reaction, and that's a process that releases heat. And I've got a little example here for you. Hopefully this prompt will work. And we've done exothermic reactions in lab before. We've done lye and water and lye and vinegar together. But this is potassium permanganate and glycerin. So don't try this at home, please.
Millions of Americans
So
have
we got to get through this ad.
Boy has all the makings of a mid-season hit, and the party.
Okay, here we go. This one's for your pyromaniacs out there. Okay, so your exothermic reaction, or a process that releases heat. So, endothermic reaction, it's the exact opposite. It's a process that absorbs heat. I've got another little video for you with an example on that. Once again, don't want to try these at home.
At least me. You guys are watching, and I don't know, maybe Jennifer is bad too because she's not too far away from it. But I promise this won't cause too much pain. It's a little stinky though. So okay, we're just mixing the sodium thiocyanate and the barium hydroxide, and we're watching what happens. Okay, it's getting a little clumpy. You can see something is happening. It's making some water. You can see it's getting kind of sticky and slushy. And if I stir this a little faster, it happens a little bit faster. It's starting to stink. So that smell is ammonia. That's the gas given off. If I had some pH paper, I could show you that. But we're going to just let this guy go. And what have you observed so far? That some reaction happened, and although you can't tell just by looking at this, it is a fairly product-favored reaction. That is, we made a lot of products, we made a lot of ammonia. Can you guys smell the ammonia? And we made a lot of water and this stuff. So this is an endothermic reaction, because basically it's frozen the water to the bottom. This is really cold. I think it gets down to about -30. This is a really endothermic reaction. So there's ice holding this beaker to this board here. So what did we find out about this? That is.
Okay, so there's an example of an endothermic reaction. Like I said, that you just need to know the terms for this module, but we will be doing calculations with this type of reaction in a future module. Okay, so let's talk about a little stoichiometry. I know that's your favorite subject here. And let's look at an example dealing with solutions. None of the stuff I'm going to go over with this part is anything new, okay? So we've got the following reaction. It says the following reaction is performed in a lab. And we've got potassium carbonate and aluminum nitrate. And we're going to get aluminum carbonate and potassium nitrate. If we have 191 milliliters of 1.25 molar aluminum nitrate added to an excess of potassium carbonate, how many grams of aluminum carbonate will be produced? Okay. Once again, none of this is anything different from what we've done before. This is just a review. But the first thing we need to do is convert that milliliters to liters. Because remember, we've got molarity there, but molarity is the same thing as moles over liters. So if I can get my volume into liters, then I can get into moles. And remember, the basis of stoichiometry, get it into moles and you can go anywhere. Okay, so first thing we're going to do is convert that milliliters to liters. So we've got 191 milliliters of aluminum nitrate, and there's our conversion factor. I'm just putting this out here. By now, all of you guys should be able to do a conversion like this without even thinking about it. So that converts to 0.191 liters of aluminum nitrate. So now we need to get to the number of moles. So if you guys remember, molarity is the same thing as moles per liter. Okay, so if we've got that, so 1.25 molar is the same thing as saying we've got 1.25 moles per liter. So we can take that moles per liter and multiply it by our volume, and that's going to give us the number of moles. So we have the 1.25 moles of aluminum nitrate. We're going to multiply it by the 0.191 liters of aluminum nitrate, and that's going to give us 0.239 moles of aluminum nitrate. Okay, so there's our reaction again. So now that we've gotten to moles of aluminum nitrate, and this one's the aluminum nitrate, and our problem wants us to figure out how many moles of aluminum carbonate, which is here, that we're going to make. Okay, so now we just look at that stoichiometric relationship. We've got 2 moles of aluminum nitrate to every 1 mole of aluminum carbonate. Okay, so we just figured out that we had 0.239 moles of aluminum nitrate. So we've got that. Here's our molar relationship. For every 1 mole of aluminum carbonate, this one here, we're going to make 2 moles, or we needed 2 moles of aluminum nitrate. Our moles cancel out. That leaves us in moles of aluminum carbonate, and we end up with 0.120 moles. Now we're not done yet because the problem asks us to have this in grams. So we now need to convert moles to grams, and to do that we need to find the molecular mass of aluminum carbonate. And all you guys should remember how to do this. You know, get your periodic table. We need to find out what the molecular or the atomic mass of aluminum is. We got 2 of those. What the atomic mass of carbon is. Now remember, we got 3 of these because you've got to multiply through in here, and then we've got 6 of oxygen. Okay, so 0.120 moles of aluminum carbonate times molecular mass is 234.0 grams for every 1 mole. And that leaves us with 28.1 grams of aluminum carbonate. Okay, nothing different. You guys use that molar, converting molarity to the number of moles in the last module with acid base. Okay. Okay, so let's talk about molality. Remember, I told you last time that we had molarity, which we learned last module in acid base. Now we've got molality. These are easy to get confused. It's basically just another unit of concentration. So this one is abbreviated with a lowercase m. Molarity is abbreviated with an uppercase m. So you want to be careful with that. Remember, I told you we had all these different m words. That's why we write out moles. Molarity is uppercase m. Molality is lowercase m. Okay, and the equation for molality is the number of moles of solute over the number of kilograms of solvent. So let's do an example of this, okay? Let's figure out what the molarity of a solution in which we've got 50 grams of magnesium nitrate dissolved in 500 grams of water. Okay, so remember, our equation is the number of moles of solute over the number of kilograms of solvent. So the first thing we need to do is figure out the number of moles. And in this case, we've been given the mass of magnesium nitrate. So if we take the mass of magnesium nitrate, everybody by now should know how to convert mass into moles. We need to get the molecular mass of magnesium nitrate using your periodic table, and you can see the conversion here. 50 grams times for every 1 mole, it's 148.3 grams. So that gives us 0.337 moles of magnesium nitrate. Okay, so we've got that. Next thing we need to do is convert our grams to kilograms. Okay, so we've got the moles of the solute. Now we need the kilograms of the solvent. And we've got 500 grams, and our conversion factor for every 1 kilogram, there's 1,000 grams. So that gives us 0.5000 kilograms. And I'm sure all of you guys can do that one in your head. Just want to write it out here so you don't miss anything. Okay, so now we need to calculate the molality. Molality is number of moles of solute over number of kilograms of solvent. And here's our equation here. We've got the moles over kilograms, and we get 0.674 the molality of magnesium nitrate. Okay, so similar to molarity, but a little bit different. Okay, so what do we need this for? Okay, there's very appropriate today on this snowy day. Okay, we're going to talk a little bit about freezing point depression. And here's the formula for freezing point depression. delta T equals negative I times Kf times molality. So all of you guys have experienced this, I'm sure. You know, cold day like today, your folks might be outside, or you guys having shoveled the walk, and then you sprinkle salt on the walkway. So why do we do that? Why do we put salt on ice in the wintertime? And the reason being is because of this freezing point depression. We want to lower the temperature at which water freezes. So if we're right at 32 degrees, and let's say we can lower our freezing point by 6 degrees, then that ice is going to melt, and it needs a much lower temperature to become ice again. So there's an actual, you can actually calculate how much does the temperature change according to what your solution you're putting in. So let's talk about what this equation means. Okay, delta T, anytime you see a delta, remember that's a change in temperature. So our delta T is at T final minus T initial, or just the number of degrees that have been changed. M is molality. We just learned how to figure that out. Kf is the freezing point depression constant, and that's something that's going to be given to you. And there's huge charts out there that you can figure out freezing point depression constant of, whatever solvent you're using. And that is the freezing point depression constant of the solvent. And then I is the number of molecules or ions the solute splits into when dissolved. Okay, that one can get a little tricky, and we're going to do a couple examples with that. Okay, so the freezing point depression constant for water is 1.86 degrees Celsius per molality. Okay, once again, that's always going to be given to you, but I just wanted you to see those units on that. Okay, so how do you figure out this I thing? Okay, so it's the number of molecules or the ions the solute dissolves into. Okay, well, first thing you need to do is ask yourself, is this an ionic or covalent compound? Okay, if it is an ionic compound, we know that when it dissolves in solution, it's going to break into ions. So we got sodium chloride here, breaks into a sodium ion and a chlorine ion. So in this case, the I is going to be 2 because we have sodium ion and chlorine ion. Let's look at this one, aluminum nitrate. Okay, aluminum nitrate, when it's dissolved in solution, breaks down into an aluminum ion and then 3 nitrate ions. So in this case, its I is 4. Now what about a covalent compound? Okay, remember, covalent compounds dissolve differently. So covalent compounds don't break down into ions. So here's an example of sugar here. If we're going to dissolve sugar into our sweet tea, the sugar molecule stays as one molecule when it dissolves. So its I is 1. Okay, and that's the rule of thumb for covalent compounds. They're not going to break down into smaller units. They're going to stay 1. So ask yourself, is it ionic? Is it covalent? If it's covalent, pretty much it's going to be a 1. If it is ionic, you then need to think about, what does it break down to? What ions does it break down to? You notice with this aluminum nitrate here, we didn't break down to aluminum, nitrogen, and oxygen. Okay, that's because this nitrate ion is one of those polyatomic ions. If it has a parenthesis around it, or if it's one of the polyatomic ions, it's going to stay together. Okay? If it's an ionic compound and they're separate like this, it will break down into individuals. Okay, so let's do an example of freezing point depression here. What is the freezing point of a solution that's made by dissolving 10 grams of potassium fluoride in 100 grams of water? Okay, so think about, what do we need to know here? Here's our equation. Delta T equals negative I times Kf times M. Okay, so we know that the Kf of water is 1.86 degrees Celsius per molality. Okay, so What about M? Do we have that? Looking at the equation, we don't. We're going to need to calculate that. And what about I? Okay, we're going to need to figure that out too. Okay, so let's first calculate the molality for potassium fluoride. Okay, so remember, molality is the number of moles of what the solute over the number of kilograms of solvent. So in this case, the number of moles of the solute is the number of moles of potassium fluoride, because that's what's going into solution. The number of kilograms of solvent, in this case, your water is the solvent. So we need to get into moles of potassium fluoride. So we're starting with 10 grams of potassium fluoride, and so we're going to convert that to moles by finding the molecular mass. 10 grams times 1 mole over 58.1, and our grams here will cancel out, and we end up with 0.172 moles. Okay, so we had 100 grams of water, so let's convert that into kilograms. You guys should be able to do this in your sleep. So 100 grams of water is the same thing as saying 0.1000 kilograms of water. Okay, so now that we've got that, we've got everything we need to calculate molality, and so we're putting the moles of the potassium fluoride over the number of kilograms of water, and we end up with 1.72. Okay, so now that we've got that, let's figure out finding I. Okay, so ask yourself, is potassium fluoride ionic or covalent? So if you look on your periodic table, potassium is in group 1A and fluorine is in group 7A. So that means we got potassium is a metal, fluorine is a nonmetal. That gives us an ionic compound. So potassium fluoride breaks into potassium and iodine. So I equals 2 in this case. Okay? Now, so we've got everything we need to calculate our equation, our change in temperature. So our delta T is negative I times Kf times M. So we've got delta T equals a negative 2, which is our I, times the 1.86 times 1.72. And so we get negative 6.40 degrees Celsius. Okay, it is very easy to forget this negative sign. Okay, so, just stay on top of that. So, what does this tell us? Okay, this tells us that our change in temperature, or the amount that the temperature changes, is decreased by 6.40 degrees Celsius. Okay, so it tells us the change in temperature, not necessarily what the new temperature is. Okay, now in this case, though, the freezing point of water is 0 degrees Celsius, so the new temperature is negative 6.40 degrees Celsius. But that might not always be the case. If you're using a solvent that is not water, that is alcohol or some other solvent, that its freezing point may not be 0 degrees Celsius, then you would need to subtract that number from the solvent's actual freezing point. I think everything we're going to use, or all the problems that you guys will have, will be at 0 degrees Celsius, the freezing point of water, because I think all of our solvents we're going to calculate for water. But just keep that in mind, okay? So think about a couple things, okay? And once you think about, would a covalent or ionic compound have the most impact on freezing point depression? Okay, so if you look at our equation, you have delta T equals negative K times Kf times M. Okay, that I can change depending on how it's broken down. Okay. Covalent compounds are always going to have an I of 1. Ionic compounds, though, on the other hand, could have an I of 1, 2, 3, 4, go on up, depending on how many ions it breaks into. Okay, so would covalent or ionic compounds give us the most change, potentially, of our freezing point? It's going to be ionic compounds. Okay, which is why you don't sprinkle the driveway with sugar. You sprinkle the driveway with salt. Sugar has an I of 1. Salt has, if we're using sodium chloride, has an I of 2. Okay, there are even better compounds out there. The more things it breaks into, the higher the I. Okay, so of these two, would sodium chloride or aluminum nitrate have the most impact on freezing point depression, and why? Okay, of these two examples, if we look at sodium chloride, we've already talked about sodium chloride breaks into sodium and chlorine, which has an I of 2. Aluminum nitrate breaks into aluminum and 3 nitrate ions, so that has an I of 4. So aluminum nitrate is going to have the most impact on freezing point depression. Okay? So last thing I want to cover is boiling point elevation. Okay? Same thing as freezing point depression. Even so, same kind of or similar formula here. We've got delta T equals I times KB times M. Okay, so in this case, I is positive, not negative. Makes sense, right? You're going to elevate the boiling point. You're going to add something to your number. You're going to decrease your freezing point. You're going to subtract something. Okay, so I is positive in this case. KB is the boiling point elevation constant. This will also be given to you. And then delta T tells you the change in the temperature. So this would be added to the boiling point of the substance. So if you end up with a delta T of 5.4, that's not your final answer, okay? Because let's say you calculated the delta T for a solution that was added to water as your solvent, okay? Well, water's boiling point is 100 degrees Celsius. So if you got 5.4, your actual answer is going to be 105.4 because we increased the boiling point by 5.4 degrees. Okay? So hopefully this all made sense and this helped out. So, as always, if you guys have any questions, you can email me, you can give me a call. This module will be due next week. And otherwise, I will see you guys in class next week, unless we have more snow.